Honorable Mr. Udaya Nirmalata Halim from BTB Foundation, Mr. Narottam Das, PhD, Speaker, Mr. Jacob Dethan, PhD, Moderator, all Vice Rector, University Buddhi Dharma, and all the attendants. Thank you. This is the international webinar. Quarterly and thanking God, I open an international webinar with the importance of nanotechnology and energy storage in renewable energy. This is the result of collaboration between the Faculty of Science and Technology, Buddhi Dharma University, with the Central Queensland University, Australia. This webinar is a series of webinars to celebrate the 6th anniversary Buddhi Dharma University. Finally, congratulations on joining this webinar. Please, thank you. Ya, silakan Dethan.
Okay, thank you, Dr. Sugiyoko, for the very good opening speech. We will now hear another welcoming speech from the BTB Foundation Advisor, Mr. Udaya Nirmalata Halim. Please welcome Mr. Udaya.
Okay, terima kasih. Thank you. It was unmute before. Okay, thank you very much indeed. So, Mr. Das, it's nice to have you to be the speaker today. Are we starting already?
Yes, please give your opening speech.
Okay. Okay, thank you very much indeed. So it's an honor for me to chip in to give a bit of speech on behalf of the Untitled Foundations, which is the head of the University of Buddha Dharma. Yes, I welcome and I really congratulate the organizing committee for conducting this a very important event, which is, to my opinion, that we are now entering the 4.0 industrial revolutions, okay, with artificial intelligence, take over a lot of manual and humans involvement in the ways of workmanship. And we know that what we touch every day, that nanotechnology is always around us. So this is, to me, is a very good event. And I thank you very much for the speaker. You've been contributing to our society, because we can't avoid that this STEM, the science technology, which is concerning of science, technology, engineering, and these maths, will influence a lot on the future generations, and also giving a lot of contributions, okay, to our life. And we do understand that 80% of the fastest growing occupations all depend on STEM technology. And therefore, once again, without further ado, I would like to congratulate the organizing committee and thank you very much indeed for your all efforts, and good luck for the seminar. Thank you. Best regard from me.
Thank you very much, Mr. Udaya, for the warmest welcome. I will now proceed by reading the short bio of our featured speaker, Dr. Narottam Das. Dr. Narottam Das received his PhD degree in electrical engineering from Yamagata University, Japan in 2000. His PhD research project was funded by the Ministry of Education, Science, Sports, and Culture of Japan. It was a Japanese government scholarship. Dr. Das has about 3 decades experience as an academia and industrial engineer in Australia and overseas. Prior to joining at Central Queensland University as a senior lecturer in electrical engineering, he worked at the USQ as a lecturer in electrical engineering. He was also a research fellow or lecturer at Curtin University, Eric Cowan University, and Monash University, Australia. Earlier, he worked at NEC Yamagata Ltd. Japan as a senior design engineer. Dr. Das is the author or co-author of 8 book chapters and over 660 peer-reviewed journal and international conference papers. Dr. Das is a senior member of the IEEE PES and PHS USA. He is also fellow of the Institution of Engineers Australia with CPEng, NER, and Life Fellow of the Institution of Engineers Bangladesh. His research interests include in power systems, communication, smart grids using IEC 61850, multi-junction solar PV cells, modeling of high-efficiency solar cells, renewable energy, and high-speed communication devices, SOAs and MSMPDs. He is a regular reviewer of IEEE transaction papers, IET papers, Elsevier Energies, other similar journal and conference papers. Dr. Das served as the program committee member of several IEEE conferences nationally and internationally, as well as presented as an invited speaker. Dr. Das is the editor of the books Nanostructured Solar Cells, Advances in Optical Communication, and Optical Communication Systems. He is also a guest editor of the journal Energy's special issues on nanostructured solar cells and Journal of Nanomaterials Hindawi special issue Nanostructured Thin Film Materials and Surfaces Engineering Applications. So dear all respected participants, please welcome our featured speaker, Dr. Narottam Das.
Hello, good afternoon. So can I start now? Can you share?
Sure.
Or have to, yeah. Okay,
Sure,
thank you
Dr.
very much.
Das.
First of all, I would like to thank you everyone, the organizer, to give me the opportunity. And Jacob was with me at USQ, so very much, he always contacted me. Anyway, we'll talk that on later on. And today morning also we talked over phone. So I think better to start our presentation. I will try my best so far I have to share with academia and engineers, engineering students. So far, whatever knowledge I have, I want to share with all. So far, even I want to learn from everyone's. If you ask question, I will be very much happy. Now I'm going to share the presentation. We start to talk. Okay. Can I start, Dr. Jacob?
Sure, sure.
Okay. All right. Good afternoon, everyone. As Dr. Jacob introduced me, as I am Narottam Das. Currently, I'm at Central Queensland University, just brief understanding. So today's, I'm very much happy to give you this talk, the title, The Importance of Nanotechnology and Energy Storage in Renewable Energy. Many we say nanotechnology, nanotechnology. What is nanotechnology? Nano meaning the 10 to the power minus 9 nanometer. I think this one everyone knows, as I got the response that mathematics is important. Of course, mathematics is important. So that one feature we are going to use. And we need energy, we need to storage it. And renewable is very much features, energy, environmentally friendly, no pollution. So far, we hope this one will be helpful and see what we can do. As already introduced to me, but my information here also in brief. I did PhD in Japan and did master's and bachelor from Bangladesh University of Engineering and Technology and Chittagong University of Engineering and Technology. It's a long way back. As about 3 decades experience. This one also written here, 28 years, now mostly 30 years, 3 decades. And at the Central Queensland University, I'm from since 2018. Before I was at USQ, that I told Dr. Jacob Dethan, that time was over there. So far we meet and we talked also this morning. So, and my features understanding is there. Also, I'm going to share the knowledge, whatever I have. We can also future collaborate with your university. If anyone interested, most welcome. We'll talk later on. Another professional on, I'm also, I did not mention here, I'm Engineers Australia Fellow, any other Chartered Professional Engineer, all of the assessor now also, so far. And I made this talk in 3 separate parts. Dr. Jacob knows about this. We shared how we will deliver. So first of all, I will talk about the nanostructure photovoltaic solar cell design for high conversion efficiency by optimizing various parameters. Because nanostructures application in renewable energy, how we can get it, that is very important. In that case, first part and the second part will be economic point of view, the performance grid tri-external PV system. I did the case in Victoria because this data I also got from United Solar. That is my acknowledgement also to them. The real data, how is happening. It could be any place, any part of the world, they can utilize it and then use it. Also, another case studies that on, of course, in Australia, optimization of hybrid solar, wind, diesel energy systems from economic point of view. That one is in Australia, Rottnest Islands. If anyone visited there, that would be good. I visited there, I know the location, how fishers are over there. It could be several places because in our community, we also want the remotely islanded people to get the opportunity for their good life. We want to share the power, we have to provide for them if even they are islanded. So far, this one is also useful. And first of all, I am giving you the nanostructure photovoltaic cell design, how it is and how possible, how can improve the conversion efficiency. I will try to speak a little bit slowly, not much fast. Then maybe someone may not get the message properly. If in between any question from any one of you, you can raise, I can stop and then I can try to answer. Otherwise, you may forget, but even 5 minutes, 10 minutes more, it's not the issue. That I have a very friendly discussion with Jacob this morning, so I will try my best. So far, this nanotechnologies application, I will give you a brief introduction and what the objective was, and background and research methodology, result discussion and conclusion. I made it 3 different parts. And then anyone asking anything? I think those are asking. Jacob, you can keep the question and then we can respond together later on.
Okay, sure.
All right. So far, brief introduction. As I said, energy demand everywhere globally. We need it. It is important. Need to solve the issue. Everyone wants energy, sustainable and featured, no interruption, pollution free. That's why solar and PV is pollution free, environmentally friendly. It is not making any noise, no carbon. That features important here. It is a promising candidate, solve energy issue. I believe nowadays many places using solar panels. However, their efficiency is the issue. That one we are talking, the solar industry faces the solar conversion efficiency. If we buy, and then if there is not much good efficiency, then people want to improve the efficiencies. That's why solar energy is very low conversion efficiency compared to the investment we did so far. Hence, there is a big research gap. We need to improve that on, and then with the same cost, if we can improve the conversion efficiency, that means we are getting the same sun from sunlight, and that one will assist to get more conversion efficiency. We'll talk about that. And this structure is a promising candidate for high conversion efficiency or solar or photovoltaic, whatever we mentioned, because they are low reflection. What you will do, Dr. Jacob, if anyone knock in your door, what you will say? You will say, welcome, come in. Why we should not say to the sunlight? This one is not written here, sorry, but this is the exemplary how we can welcome the light on the substrate, that is on the surface of the panel. Then welcome, come and talk, very sweet talk. That's why we are using this one. I talk this one in different places. They are very happy to know. That's why we have to consider the surface corrugation, different types of shapes act definitely incident light, and they are welcoming the light. I will show the structure and how it would be featured application of nano structure or nanotechnology, whatever we say, that is important. So this gap, and then we have to improve the conversion efficiency. We considered this structure for optimizing the parameters of nanostructure gallium arsenide solar cells. It could be any other type of research is ongoing. So this study for different parameters, how it affects, how the conversion efficiency can improve, but we should welcome. Don't say go away. Go away means it is reflection. I cannot say that one. We should welcome that one. And then the simulation results obtained by OptiABD software. I will briefly explain in that software. That is also a student version is freely available. Student can use it, but not for the staff. That is the company rule. If university want to start, university staff want to use, I have to buy it. But any other places also to investigate the most efficient nanograting structures for the gallium arsenide solar cell to capture the light into the substrate efficiently and improve the conversion efficiency. That is the purpose. Background, different structures of PV cells. We will consider anti-reflective coating for the reduction of light reflection, nanograting structures shape. And then I think this one is very much featured and well known. We know this is a cell, solar cell, and its module. How the module forms, this is a simple matrix. As we, Mr. Udayahalim said, mathematics is required. Of course, mathematics is required. This is 3x3 simple matrix, 3x4 matrix. And then couple of module, again, as a matrix form, usually panels, if you see there are sections and sections, they're making the array. This is very simple talk, but how it comes from simple on cell, and on cell is simple PN junction for solar cell, diode model, and so on we are using. So solar cell is a device that can convert light or photon energy, sunlight, directly to electricity through the PV effect. That one we are going to use. So far, if we consider that anti-reflection coating, what does it mean? Anti-reflection is coating when sunlight is coming on a substrate or plane, then light is reflecting back. You can see it here, light coming, reflecting back. That means not much oil coming here. If any question, feel free to ask me. And then what we can do, we want to put some of this additional materials on the substrate. You can see this is a like a pink color, something additional material on the substrate. Then this light reflection reduced comparing here. I think it is clear. And then whoever, myself and whoever we are using glasses, you can see the example every day we are using. I am also using. If I off this on, I cannot see properly. That means light reflection is an issue. So we don't want to reflect mass and get on. That one we need the aid something, as here needs something features materials, here also need that glass. And that coating level is there. So this on right side on from me cannot see properly. This one can see properly. I think this and this layer is of course nano scale. That one we are talking today. And then if we go for this and the nanostructure, how it is, we can compare this one with the moth eye. Moth and simple insect, we can see, they can see the features and they can see in night time. And then see here, we cannot see properly, but here, and then see, sorry, and then how the structure is going on, we can see it properly, and then bigger way, and then bigger and bigger, how the structures are here. So far, this is a multi-layer anti-reflection coating, and light repairing property is high. Moth eye principle is very much useful. Similar on paper we published myself and my supervisor earlier. And then this nanostructure is embossed on the surface of the solar cell that I said the previous example as a mathematical one. And this one reduces the light reflection in the wide range of wavelength. We have the solar spectrum that on depends on the which material we are going to use. That's why we also need multi-junction. We don't talk all over, but so far that one is important. And if we see here, this structure, sub-wavelength grating structure. And then here we can see how the light reflecting back. This one is a rectangular shaped. I will explain in this later on how the reflections too much high. We don't want that on. As I said, we cannot say go away, come in, or how can I help you? That is should be our features. And then triangular shape, and then this is the hairstop or trapezoidal shape, and this is the triangular shape. The deflection is very less here comparing. This one indicates how the reflection happening on different structure of the cell on the surface of the substrate. So far, subordinate features cause gradual change, because if subordinate, the gradual change, and which act as a multi-layer anti-reflective coating leading to low reflection. See, low and low. But to make this one also difficult, has very difficulties, so, but we can take care, hairstop easily can use it. And then the nanostructures act as a anti-reflecting layer. Triangular shape was the better one as a multi-layer. So far, this three structure is very much useful. In between, there are others, even different types of trapezoidal or hairstop cone structure it could be. That one depends on the work, whatever we are doing. And we also compare the anti-reflective coating. If you say rectangular shape, then see how the light reflection is happening in grating zone, how the structure changes. But if triangular, then this will change very smoothly. Even in between hairstop, then it will be minor change, and that is not a big issue. So far, rectangular shape structure shows that reflective index changes very sharply. We don't want change very sharply. We want gradual change in the grating zone or grating structure. The deflection loss we can calculate using Fresnel's equation. This is the feature equation. This is N1, N2. Two different medias, refractive index. So far, nanostructure grating geometry is rectangular and triangular, so they are doing gradual change. So rectangular is better or hairstop. So that mathematics also required. And then we want to simulate, as I say, to model. How to do that one? We need mathematics. So I very much appreciate Professor Halimuda has said mathematics is important. So I don't know, before talking, he mentioned, so we need to know the mathematics. And then this background coming, of course, from mathematics. Science and mathematics is important. They are coming from two different equations. Scientists actually, Lorentz and Drude dispersion model. Lorentz and Drude, whatever they discovered, that one, we are talking the complex dielectric function of metals and surface plasmon is there, structure is there. This on as a epsilon r, there is relative permittivity with the free electrons and bound electrons. This is the combination. And this free electrons part is invented by Drude. That's why we know from physics, this is the model of Drude. And this one with the bound electrons on found by Lorentz. Then it is Lorentz model. And then combining these two models, then can be combined and expressed as a Lorentz-Drude model in general. So this one is featured, we used for the modeling and software. And then finally came back to ability simulation on, and then Maxwell's equation is here, and this is the advantages part. We're going to use this one, and we are going to use this software and then simulate and get the simulation results. It is a powerful simulation and modeling structure, and ability to light transmission, absorption, reflection can calculate. That is for solar cell that we are talking, the nanostructure solar cell. And engineering simulation tool for simulation, it can be simulated for solar cell, photodetectors, any other corrugated surface also. So software is here, comparing the surface results, and finally getting the nano-grating structure parameters that we use. So far, here, if we show you here, rectangular shape, you can see, as we explained the mathematical model or formulation, this is triangular, and then pillar structure, we made it here. So far, we compared this structure and then found what are the features on. So this results triangular shape, pillar structure, trapezoidal, and compared these three structures, and then various parameters we obtained. If we see the results for triangular shape, we have compared the light reflection for different structures. And then what we varied? We have varied the thickness of the materials that we put on top of the surface. Then about nearly 300 nanometer, we got about 2.6% of light reflection. As flat type substrate, this could be 30%, but I can say about 27% we have already welcomed light come into the substrate, whatever we want to do, and that on will improve the conversion efficiency. The next result showing trapezoidal on, this is about 0.8% light reflection with the similar feature 200 to 300 nanometers. That one would be very good layer on top of the surface. I think Dr. Jacob can share slides to others whenever we finish the presentation, because we're talking a bit faster, otherwise cannot finish. And then if we use the reflection calculation for pillar shape structure, then we found the featured on about 0.5% light reflection. That means most of the lights we welcome inside the substrate. So reflection loss reduced is confirmed. And this is very features result so far. And then we compared whatever we did, the trapezoidal, triangular, and pillar shape. We can see the pillar structure, triangular shape, and rectangular. This optimization pillar on is better. And the triangular are also giving here, but different wavelengths, these factors also there. So far we compared, and then all are very close, but in reality, this is modeling, but when you do the experiment, there will be mixed type. So we can expect 2-3% light reflection because different types of features will happen during a lithography process. So this one concluded that we can get light reflection for pillar 0.5%, triangular 2.6%, and trapezoidal 0.8%. But light transmission and absorption also, these features are important. So we can consider the nanostructure. That one will improve the conversion efficiency. So this one says light reflection 0.5%, and which gives about 38% lower optimized result. And this one is maximum light absorption calculated 58% for trapezoidal shape. And the simulated result shows the reduced reflection loss can confirm the light can absorb by the nano-getting structure into the substrate, and this shape will improve the conversion efficiency for gallium arsenide solar cell or any other type of solar cell. That is very much useful. So far, later on, I'm moving to another task that we did, economic point analysis. That is, as I said, the Victorian case. Objective, introduction, location, load profile, methodology, economic parameters using Homer, as I said, economical comparison and technical comparison and conclusion. Here, use Homer software to simulate an economical point of view. We have calculated and understand the system performance and evaluate the impact of different types of configuration that can be considered for optimization. This is the load profile for a specific location. And this location is Coronet Bay in southeastern suburb in Victoria, Australia. But it would be location-wise, maybe Indonesia a little bit different. Depends on the sun, irradiance, and other features also, and geographic location-wise. So in that particular case, they need about 4.1 kilowatt hour per square meter, as shown in this figure. From January to December, the results are here. So far, and then we got the load profile. This is for a day, the 7.08 kilowatt to 38 kilowatt hour, minimum and maximum. And then this is for the profile for the year. Then we consider the different cases. This case will give the first case, we just consider directly. And then later on, we got this the system with the grid and then how it should be. Then we have simulated for case number 3 with battery storage. Battery is important. Features are here and then connected with grid and then hybrid inverter is required. Then number 4, we have the battery and this storage and capacity. And then this is the grid configuration type. And then we are going for diesel generator, but this one will be a bit expensive. We will discuss that one. And then with the battery and then storage system, and we use this Homer simulation software. As I said, student free version, anyone can use. And this on lifetime is about 25 years and fuel price is $1.44 per liter. And the solar panel cost is this, and then depends on the cost in your local market. So lithium ion battery also required. And then, so if we compare the different cases, then we can see the Australian dollar per kilowatt hour, how much the cost. And this one, I believe the case number 5 is a bit high cost, is not recommended. 6 also high. 1 is also different. And then 2, 3, 4, we can consider, but then 3, 4 is more useful on, and net profit cost also we have to analyze. So how much the cost for empirical comparison. Then 5, 6 is also not recommended. That one is the Fisher result said. Here also we have to think about the economical point of view here, but also carbon emissions cost. So as we have done the 6 cases, 6 is not possible. And then 1 is also, there are issues. Then payback period time, as we cannot pay continuously, how the time period is required. This is the Fisher's time period. And then compare the technical comparison, see energy from grid and energy to grid. How much we are getting from grid, how much we are giving to the grid. We need to minimize the cost, otherwise it would not be feasible. So in this case, if we think about the liters per year, how much cost for the fuel, 5 is not recommended. Then technical comparison, carbon emission is another issue, because if too much carbon, that one is not useful. Here we can see the number 5, emission of carbon is high. As I said at the beginning, we want environmentally friendly. If emission of carbon, that one is not enough good. So far, in that case, 5 is not. And then mainly 2, 3, and 4. And then see the analysis said 2 and 3 is better. 3 and 4, 3 is more preferable. So that's why in this study mentioned that in realistic case for residential area demand, as we said in Victoria, Melbourne, but as I said, in other places, Indonesia, Malaysia, or any other places, it could be different. So case 6 is not feasible, that I have given the indication, and does not reach to payback period for the project lifetime. So we don't recommend for 6 cases, and case 1 is still expensive and no payback resource. It is therefore any grid fault or power outage would be happen, but case 5 is cheaper. There is, it is not recommended because due to the carbon. So we recommend case 3 and 4, and this one is still cheaper and useful than 1. So this one is recommended. So far, later on coming to the optimization to the Rottnest Island, as I said at the beginning. So optimization solar, wind, diesel, including the hybrid system, economic point of view. We want to save the money, every place is the resources, and minimum cost. This on aim, introduction, and literature review, methodology, discussion, and conclusion I will present. This one is useful because we are using the levelized cost of energy and greenhouse gas gases using Homer software I mentioned, and design this system, hybrid system, solar and wind, primary source, and diesel is secondary energy source. We don't use energy much, but for modeling hybrid system, field data collected using the Homer software, and minimizing the net present cost and generation of cost energy using the Homer software. So far, solar, wind, diesel system, hybrid system, net present cost is the importance. So hybrid system is the best alternative of non-renewable energy sources, less fuel price and reduction of emission of gases. And Homer is using for simulation and optimization of the cost and drawback, common to solar and wind power generation, and their unpredictable nature and dependence on the weather and climate change. Because if we don't have enough sun, solar cannot work properly. Even there is no wind, that time wind is also the issue. That time diesel cost may increase, but we optimize that on how we can utilize it. That is very important. So far, this is the block diagram for the flow chart, how system is working. Flow chart for hybrid power plants, solar, wind, and diesel. Everyone is interested for this one, especially off-grid, and then if you want to generate by your own. So I'm not describing the block diagram. So this on the combined solar, wind, and diesel system. And then for this design, we have to consider the renewable energy sources. These are the photovoltaic and wind energy, and then non-renewable diesel. And another on battery bank, that is storage is required. This is something part of our talk today. And then bidirectional converter is required. So this is the block diagram for a hybrid system. And this one is how we accommodate wind. And then this is the dummy load and diesel configuration. And the battery storage and PV module is here. If we look in details about the location where we consider Rottnest Island, if you see in this picture, this is Australia, and then here is Rottnest Island. Inset figure you can see here. I visited there. It is a nice place for the day tour over there. If anyone interested can go. And this one they required about 18 megawatt hour per day, 1.2 megawatt peak load is there, and there is monthly demand, how much, peak average, and then solar radiation, there wind energy, and geographic location. Just to say where is the location, it would be very, as I said, location-wise. So far, available renewable energy rate at Rottnest Island in Western Australia, that one is monthly average solar radiation here. We can see January to December, but here, May, June, July, August, we are not getting much. I think Indonesia is a bit different, right? Comparing Rottnest Island. And here, monthly wind speed, mostly we are getting, but that one is useful. But this is the Homer Pro-based data. And Homer software, as I said, developed by NREL, and Homer for economic analysis. This software is used to simulate and analyze and optimize the electrical system. And this one process for combination of each configuration and display list source and net present cost as mentioned. This is the diagram. Input side, what we are doing. Software is here in your computer, output you will get. And then, of course, input side from realistic data, how the features. Then simulation of hybrid system. Here also we have the different cases, about a couple of cases. And then we can see this case, we say generator capacity, PV, and storage on, and then wind turbine system converter, and then in this case, the simulation and architecture hybrid for the community load, how the community is using over there. Then from the simulation for this case study, we are using 50 size, generator 50, PV 20, storage 150, and then wind turbine and the system converter. So here we have the diesel system for community load. And then simulation result says and discusses that monthly electric production, how much, and then comparison of the production and percentage wise. Here the rate about 47% from PV, and generic the fixed capacity that is 33%, and 3 kilowatt or 50 kilowatt, this one, and 3 kilowatt total, we are getting about 100%. So quality wise, excess electricity value, and then demand and the capacity of storage. So far, and then sensitivity analysis, this is especially for Rottnest Island, and I'm not going in details for this one. This one, the feature data, that is the one. And then we got the PBN wind capacity, and PBN wind that time, we can say that here the production, total production and unit, and then maximum output, and then quantity, the production, and so this is the feature on for PV output, and this is the wind output. We need combine as we want to do the hybrid system. So depends on, because wind is there because it is isolated island, and then battery output here. In this case, the battery depth of charge for load as lead acid can be up to 80% and 20% charge remaining. Battery stay full charge most of the year because that will need your storage. As I said, in case your sun is not there, this is unpredictable due to the climate issue. Also, wind is not there, then it would be, that's why I need to continue a charger situation also. During the month of flow production from hybrid, SOC reaches to 30%, and the system converter said system, this is the features, system inverter output and converter output. So we can see inverter and a rectifier and units. So how much you are getting, 740 is the rectifier on kilowatt per hour. This is the losses on, and then if we go for the cost analysis, we can get, this is the total cost analysis for this specific case. Any case is different, then it would be different. So for emission wise, carbon dioxide, this amount, only for diesel, this is very high, I think, and this one is less, hybrid system. That is, hybrid is recommended. So 21,000 kilogram per year. This one is 117,000. So this is the issue for only diesel, but carbon monoxide is this, and the hybrid system is here. And then unhybrid, unburned hydrocarbons is this, hybrid is this. And then particulate matter for this, and then sulfur dioxide and others. So comparing, we are getting less carbon dioxide, less carbon monoxide, unburned hydrocarbon, particulate matter, sulfur dioxide, nitrogen gas. So it is recommended that this hybrid system is better. So as I can say, finally, the solar wind diesel hybrid system is the most effective in relation to the net present cost or cost of energy compared to other hybrid system. This is the predicted on with the realistic data, offering the cost-effective simulation solution as well as a smart system and a smart, affordable climate solution. Hybrid system disregard the diminishing of lot of greenhouse gases which are produced from a thermal power plant. So in last, hybrid system gives remarkable changes in the energy production for all over the world. So this one is really useful. And then finally can conclude, nanotechnology is important and useful for renewable energy design and performance analysis. And we confirm the nanocoating structure can improve the combustion efficiency. That one will help for environmentally friendly situation, as well as grid tie system. We said that the different cases, 3 and 4 is useful compared to others and feasible or levelized cost of energy stream is cheaper. And hybrid system is the recommended one. So that one will give you effective cost-effective relationship in relation to net profit present cost and cost of energy compared to the combination of hybrid system. So we recommend that one. Finally, the hybrid system include energy storage, provide remarkable changes in energy production around the world. So we recommend the hybrid system, including nanotechnology and so on. So finally, I acknowledge to my school, that is School of Engineering and Technology, CQ University and Center for Intelligent Systems to support me for research in Victoria. As well as I got 2 companies' data, the realistic data that I mentioned, that is the solar energy Hallam in Victoria, and their continuous support to complete the task. And all the postgraduate research scholar colleagues who are with me to conduct the project, research, and publish papers. Also, I would like to thank you very much, Dr. Jacob Dethan, the moderator, Dr. Sofian Sugyoko, the rector, and Dr. Engineer Amin Chwinto, Dean of UBD, for organizing this webinar, as well as Mr. Uday Halim, as mentioned, many things about mathematics. So thank you very much. Terima kasih.
Thank you very much, Dr. Das.
And any question and comments, feedback are welcome. As I said, happy to share the knowledge. And my contact details are also here. Thank you. Terima kasih again.
Once again, big thanks to Dr. Das for sharing this very useful and interesting lecture. We have several questions here, Dr. Das.
Yes, please.
Okay, the first question is, how cheap is nanotechnology for solar cell?
Okay, how cheap the nanotechnology for solar cell? Very good question, very important. Initial cost is a bit high, but for long time run, this is useful because initial on need support. That's why different countries, even in Australia, we are going to install even my house, the solar panels is coming hopefully next month. Under stage 4 lockdown, we cannot do it. The government subsidize here about 60%. Need initial support from government, then it can be used. So government support for this one is important. Even university, like you are an academia, you need support. If university and government can support, you can proceed for better on. Initial cost would be high, but for long term, for future next generation, better to proceed now to improve the conversion efficiency and get better environmentally friendly. Otherwise, carbon is there. It will affect the nature, affect birds, plants, trees, everything. Like this coronavirus, it's affecting our normal life. So I think move to nanotechnology even needs support, that I would say. Even the software is also expensive.
Okay. Thank you, Dr. Das. The second question is we have here, is nanotechnology has negative impact in our life?
All right. So, nanotechnology, like smaller and smaller, then so far I know not much affecting, but like mobile phone, smaller and smaller, using, even though, as I mentioned earlier, I worked at NEC Japan, I made like 4G mobile networks chips. NEC Japan, but the 5G network also, there is also different effect, but I think the renewable energy side, this one is not much affecting from up to now. In future, it maybe need to be investigated. Whenever you do the research, you have to do the health and occupational health and safety things, features we consider, even Australia and any country. I think it is not much, but there is about, if you ask, how about the solar panel maintenance and cost also there, because if dust is coming, that one also something impact, but that one is possible to maintain. But I think not much effect on life, but if we are using mainly for energy side, but photo detector and light emission, it may some issues, but it is under investigation, not right now. But we don't do anything about that on effect. Whenever you submit a paper, 3-4 reviewers will look and then see how the fees are, how it is benefited. We will think for community and future generation.
Okay, thank you, Dr. Das. The next question is, how hard nanotechnology to be mass produced?
All right. So currently it is producing in many places, because you can see, as I said, upgraded device, many places is coming. But of course, nanotechnology fabrication, you need, for example, I used focused ion beam lithography system. I was at Economical University, then I was in Korea, I was in Japan. Of course, a little bit hard, but not impossible. Need good concentration. As I said, and Professor Halim said about the mathematics, that mathematics knowledge is important. You cannot make difficult on. Of course, it is possible, doable. Nanoscale features are useful. Even now, sub-nano, people thinking about sub-nano in future, they don't want to do. Like 10 to the power minus 10, that would be 0.1 nano, but still investigation. It's possible, doable. Like before we say femtosecond, now attosecond, femtojoule, attojoule now, people thinking about this.
Yeah.
Not hard, but need to think. Maybe our next generation will do better than us, I believe.
Yeah.
Okay,
thank you, Dr. Das. Very good. The next question is, what is the best nanomaterials for solar cell?
All right. Based on that one, you took me, I have to give another presentation. All right. So I will send you the slides separately, but I will give you the understanding. Yes, I finish, and then Dr. Jacob, you can give some chance to Mr. Uday Halim to ask some question. I'll finish this one. Gold and silver usually using, and aluminum also using. I use mostly gold. That's why Japan say kinset, kin fiber wire. I have tested that machine. I was NEC for the design engineer that I mentioned, and then silver also using. Gold we cannot use always, but gold performance is good. Silver using or any other thing, but materials to materials and combination, it will vary the efficiency and results, performance.
Okay, thank you very much, Dr. Das. Maybe one last question. There is a question, how about the development of hybrid system in Australia?
All right. As I said, rottenness is there. They are using, and other places. I have another student at USK, when you were there, they are working on Queensland islanded place. I forgot the island's name, and I was the examiner. You know, my room's next, Andreas was the supervisor. I should examine that one. Yeah. Many places, islanded places in Australia, they are using. Even Japan, different places like Sado Island. That's why I asked, even Indonesia, there are different islands. They can also use it easily. So that one also possible. Australia using, other countries using. And one of my work, myself, my research associate and collaborators is going on. After 2 months, it will be published. Or I have one now I can share with you for details understanding. So that would be also useful. So it is going on, hybrid system, many places. That's why I want to install in my home the solar panel, then little bit electric bill issue, minimization of cost. And then I think I have the opportunity, as I got Engineers Education Australia Fellowship, I have visited different places, how we can transfer energy. I'm not going the transmission system, bus link, in Victoria and Tasmania, Kings Island connection. Yeah. So far, you are also power, and you are in my power system analysis. So far, that is it possible, and it is useful. That's why we have to think about this. Yes, please. Thank you.
Thank you very much, Dr. Das. I think that's all for the questions.
But now, Mr. Uday Halim want to ask something? Could you please give follow?
Okay. Thank you very much indeed, Dr. Das. I really appreciate what you've been giving. And you keep on mentioning about Rottnest Island. Okay, I hope your project is not disturbing our quokkas there. Okay.
No,
I live in Perth. No, I know. Okay. And I thank you very much indeed. Okay, I live in Perth myself now. I'm currently in Perth. Okay. And thank you very much. It's an eye-opening, whatever you talk. So I would like to give a message to all others, I mean students especially, who are coming from different backgrounds. I'm not from math myself, okay, but whatever is introduced by this nanotechnology is turning the pyramid upside down. So any question is asking about the cost, you are in the middle. So what is introduced by Dr. Das to me is how this pyramid, okay, with big capacity, with big investment, small capacity, the nanotechnology is turning from small investment with a bigger capacity. But of course, to change entirely drastically is not that easy. And that's why, but the message is crystal clear to everyone. I learned by myself today, okay? I look at a lot of things that accountants should consider, okay? Other backgrounds should consider how you balance this technology. Otherwise, everybody will be just left behind. Yes, so I really appreciate what you've been giving us today, eye-opening to me, okay? That with a smaller technology, but a bigger impact. So when questioning about the pricing, and I'm very sure it's just like the very small, maybe very common sense and a common analogy is that in the past we talk about even chips, okay, for the computer chip, okay, how big it was, okay, and now we also come to the very nano size, and that kind of technology should be really eye-opening for those even not from engineering department. So that's why my message to all the students, because I noticed from the questions, a lot of people say, I'm not interested, or I'm not, okay, in the field. I'm not in the field myself. So a last remark again from me. Thank you very much, Dr. Das. I hope I can see you in Perth here, okay, Eddie Cohen or Curtin. All right, thank you very much indeed.
Thank you very much for your appreciation and explanation. Yes, initially when I started, even to be honest, I did before and I measured myself at NEC, even though I got NEC award for measurement and testing of semiconductor devices. That one is linked with this nanotechnology, as I was there, that was in 2001, after finishing my PhD when I worked there. And then I have a little bit understanding what is happening inside. And then I have seen myself, if you just a little bit talking the physical example, if you cut your skin, what you can see, morphological structure, biological, ontological structure, doctor can understand. And then I have seen myself that photodetector, as Jacob mentioned today, and also solar cell structure with my students under the furnace and lithography process in Australia and Korea and Japan. Then you can see what are the mountains are coming. But of course, nanotechnology, that one we magnified whatever the size, then magnify 1,000 times or 500 times processing time. That one I did. If I think I can give some of the real results in published paper, and if your university anyone interested, Jacob can contact me. I can share that on, and these slides also Jacob can share. This one is between myself and Jacob was, as I said in my class, so very much cooperative, friendly, and now we are all collegial. Sorry. So far, definitely we will share the knowledge. Even I can learn from students. Sometimes this something also my students explain to me, and then I have guided and create the new opportunity, new way of life. That's why nanotechnology is important. Storage is required. Future will change. That's why this is important. I'm happy to share anything required from my side. And if anyone has any question, my contact details are here, and they can email me. Then I can cooperate and support as I have knowledge to share with engineers, engineering students, academia, science, or any other person want to know. Most welcome from my side.
Thank you very much, Dr. Das, for this fantastic Q&A session. Now we will have the closing speech by the Dean of Faculty of Science and Technology, Doctor of Engineering, Amin Suyitna. Please welcome Dr. Amin Suyitna.
Dear participants, thank you for attending our webinar. We didn't expect that there will be so many enthusiastic visitors for this topic. There are about 1,000 of people who have registered themselves on our list, but due to limitation, less than 100 participants can only join us via Zoom. This means that the topic is very popular and many people are interested. To be honest, this is my first time listening to a subject about nanotechnology because it's different from my research interest. I didn't know before, and I don't know how important nanotechnology is in the present and future. It's nice to know so that we can open our mind to understand technological development from now on. So we also have to say many thanks to Das Sensei. We know you graduate from Japan, and also we know that you influence in speak Japanese, I think.
I can speak Nihongo dekimashou.
Oh yeah, okay. Yeah, that's why I call you as Das Sensei. I'm also graduate from
Amin Sensei, most welcome, no problem.
Okay. I'm also a graduate. Yeah, I'm also a graduate from Muroran Institute of Technology in Hokkaido.
Hokkaido, when you graduated?
Yes, Mumbuso.
Mumbuso, yes.
Yes, when? Yes. Where in Muroran, Hokkaido.
Okay, Muroran, which
when?
Yes.
I came in 1987 up to 1984.
1987 to?
1984.
Okay.
1994. Sorry.
Yes, I went to there in 95. So just you finished and I started.
Oh, really?
And I finished initial time, Saisho wa Kenkyu se research student, then PhD student, and finish in 2000.
Yes.
Before finishing my PhD, I got job at NEC. That's why I went to NEC. To be honest, as Mr. Uday said, I am not mathematician, but need mathematician. We know mathematics. We can do mathematics. Chugaku dekimasu. But we know the real engineering, practical engineering, how it works. In my hand, when I did work at NEC, 8-hour job, 6 to 7 hours I am in the lab. See what is this, how it is. That's why practical hand is important. Practical engineering knowledge is required for everyone, all of us. Whatever we know, someone less or more does not matter. We have to work together and then improve. That's why I went to there. It is really good experience. And you may think, that's why during my lecture, I always give some practical example, where it is, how it works. That's why I think, Sensei understand how it is working.
Yes. It is similar with me, because when I come in first in Murora, also as a research student, it's not in a program student, but a research student. That's why I finished my doctor, my BSc, and there is take around 7 years.
Yeah, that is very normal, because that the Kenkuse research studentship. Sorry, Jacob, a little bit going longer. So that one is very useful to get the base of research.
Head.
Thank you. Research studentship, and then like L-plate to P-plate and run as express. That's why I published FIEAust work. You can get from Google Scholar, and then worked hard, and now I try to help my students. I'm trying, and every year, this year also, about 6-7 journal published, and 3-4 will come tomorrow or day after tomorrow. Hopefully, get another acceptance. That's why we are working together. And if anyone interested to collaborate, most welcome. That is also helpful.
That's why we hope that Buddhi Dharma University relationship with you is a continue into the future.
Sure. That's why before Jacob contacted me via LinkedIn, and then initially I remember, and that's why, and then long way back, and then he is contacting. He also wanted to do PhD with me.
Okay.
And then somehow he went to Monash. That's why Monash also good. I was also Monash in 2005 to the end of 2004 when I came in Australia. Then until 2009, I was at Monash Clayton, Victoria. Then went to Edithcon, Curtin, and then USQ. And then we are trying. So far, I have knowledge. We can try.
Yes. Anyway, that's Sensei. 本当にいろいろ
先生、本当にありがとうございます。
いろいろお世話になりまして、心から本当にありがとうございます。
本当にありがとうございました。どうもありがとうございました。
これからもよろしくお願いします。
どうも。
また会いしましょ
う。私も連絡します。I also will contact with you and then Jacob, and for any future, anything we can jointly together help each other.
Okay.
Another lecturer, Higashi Timur University, I lost his contact. He was also my student at Curtin. One time he asked me, he is teaching the same before. Also, Jacob knows I taught power system analysis and communication at USQ, and he is teaching communication at Higashi Timur University something. And he said to me, "Sir, can I get your lecture note? What do you want to do?"
Okay.
I am teaching this one. I want to follow your standard. I said, most welcome. I will give you the PowerPoint presentation. Just change your name and then you can deliver. That would be great for the future engineer and future community. That should be our objective and motto for future engineers. We have to develop them for future generations support.
Okay.
If I am not after 10 years doing anything, learn from me, they can deliver to the next generation.
Yes. Okay. After we talk and we prepare with Mr. Jacob.
And then I think, Jacob, you can share these slides to others, whoever, Suinto Sensei or anyone interested for the work on EP in your network, that should be fine. Just for their academic use, not for presenting anywhere. That is the request, confidential use.
Sure. Thank you very much, Dr. Das. And
thank you very much.
Yes, we would like to say great thanks to all the participants from all over Indonesia, On behalf of Universitas Buddhi Dharma, we hope we can see you again in our future webinars. Many thanks to you again, Dr. Narottam. It is a pleasure to have you.
Okay, thank you very much. All the best for everyone.
Thank you.
Okay, brother.
Keep in touch.
Terima kasih. Sampai in Perth.
Arigatou gozaimasu.